This is lecture number 14. Let's begin with the summary of the previous lecture. In the previous lecture, we started with the introduction of the Deutsch's algorithm, and then the most important point I wanted to emphasize with the Deutsch's algorithm is that it has a typical pattern of the quantum algorithm. What I mean is the following. So the question is, what makes the quantum algorithm better than the counterpart in the classical algorithm? And then probably most of the quantum algorithm generally starts with the initialization of the qubits. Then we try to create the superposition of all the maybe all or many of the multiple possibilities. Then the processing part is similar to the classical counterpart. So the challenge here is we need to implement the um, equivalent circuit in the in using the quantum gates, and then once it is done, then we generally need we eventually need to make some measurement from of the output. But before the measurement, we generally need to go through the interference of the multiple output. If there was no such if we don't do this kind of interference, then the result of processing is the superposition of all the um, possible inputs, and then there is no even though all the output state might have some information about the um, output value, that if we just measure it directly, then only one of the output will come out, and then you have to repeat several times. So that won't help us. So typically, right before the measurement, we should do some interference part. And then, depending on how you describe the algorithm, sometimes this interference part might be included or embedded in this processing part. But again, if you don't have this kind of interference step, then you cannot get the proper speed up. And then to explain how we can convert the typical digital circuit to a unitary gate, I explained further detail about the reversible gate. And then there are a Toffoli gate or the Fredkin gate, which can be used as a reversible gate. But then whenever you use those general gate, then we had the problem of auxiliary qubit and then garbage qubit in the output. And then the problem with the garbage qubit is that it is generally entangled with other qubit, which contains the information for the result, and then they generally need to be in superposition. However, if this garbage, some of the garbage qubit gets measured by accident, then it will be detrimental to the entire result. So yeah, it is important to protect this garbage qubit, or more the better way is uncompute, meaning somehow unentangling the garbage qubit from the important qubit. And then once it is done, those garbage qubit can be used as an auxiliary qubit for the further processing. And then now, I started to introducing the factoring algorithm, or so-called as a Shor's algorithm. And there are two important factor where a component which will allow us to achieve a quantum speedup. The first component was the simultaneous calculation of all of these type um, for all x from 0 to 2 to the log 2 base n, and then this part is similar to this part in for generating the superposition. And another part was the fast Fourier transform, and this one corresponds to the interference part of the Deutsch algorithm. And yeah, let's review the factoring algorithm in more detail, a little bit more detail. So the factoring algorithm goes like this. And then, yeah, there are again, there are two important components in the factoring algorithm. And then that components are also represented in terms of the circuit in here. And then the first part is that we have to create all the superposition of all the possible value for the exponent or power of this r to the a. And to generate the superposition of all the value from 0 to 255, what we do is we prepare the ancilla register, and then all of these value will, by going through the Hadamard gate, we will create the superposition of all the possible value from 0 to 255. And then we will also initialize the encoded register. And what we do is we actually calculate this part for all these A. And then so this unitary part corresponds to a calculation of the R to the A mode 15, or whatever n value it is. And then this operation is controlled by the value at the ancilla register. And then all the superposition of these result will be available at this point. And then finally, what we do is applying the quantum Fourier transform. And then this quantum Fourier transform will be applied to the ancilla register. And then maybe you are not familiar with the concept of the quantum Fourier transform. So I will work on the detail in the next pages. In this algorithm, we are using notation like small n, and the small n is actually obtained by the so it is if we want to factor number 15, and then we generally use the capital N, and then we want to figure out the minimum number of digit, binary digit to hold this information. So to calculate that one, it is basically log base 2, and like this one. Then this for the n equals 15, n will be something like 3 point something, but we need some integer digit, integer number of binary digit. So we will just take something like ceiling function, or something like this, and then it will become number 4 for capital N equals 15. So this is the definition of the small n. And then why do we need small n qubit for the encoded register? Because eventually what we are going to do is store the calculation of all these remainder. So I just want to remind you that this table was obtained by applying calculating R to the zeros, and then R to the first, R to the second, and R to the third, and so forth. So here our example used R equals 7. So it is R to the 7 to the first, 7 to the zeros, and then 7 to the first, 7 to the second, and so forth. And then the value appearing here is not a direct calculation of this one, because this one should be 49, not 4. But what we are writing down here is the right after we calculate the R to the 8th, we have to find out the remainder when we divide this number by number 15. So these are the remainder. And then just to remember that we had pattern of 1, 7, 4, 13, and 1, 7, 4, 13. And so there are period of 4, and then these were the result. And then finally I want to go back here, and then whenever we calculate all these value, then we need to contain or store this value in some of the quantum register, and then this encoded register will hold this value. So we know that this remainder value cannot be larger than number 15 or capital number n. And so if we have the small n qubit, which was obtained by this calculation, then this amount of register is large enough to hold all these values. So that's why we are using this n. And then the reason we are using 2n is it is related to the result of the quantum Fourier transform. So we can discuss it later. So this is what we are going to use for today's discussion. So let's analyze in more detail. So what we need is the first thing we need is the superposition of all the possible value. So we need something like 0 plus 1 plus and 2 plus up to 255. So do you remember how we can create this kind of superposition of all the values? Well, you start with the initialization value of 0, and then you apply the Hadamard gate for each of the qubit. Then you will obtain the superposition of all the value within the range. And what about the encoded register? Again, the purpose of the encoded register is to hold the remainder value after we calculate these. So before the calculation, generally this part will appear as some kind of unitary operation. So initially we generally prefer to reset this one to 1. And then, so the quantum state right before it will be fed to the this main part. This is the tensor product between these two qubit or register. And now what we are going to do is apply this operation. And we know that if we have this tensor product, then it will appear as the summation of all the combination of the tensor product. And then what is the first term? Well, the first term is that the result of the calculating using this value as an input. And then for this example, we are simply assuming we are using r equals 7 again. So in that case, we know that 7 to the first, 7 to the zeros is 1. So this 1 value corresponds to 7 to the 0 mode 15. And then what is the next term? It is obtained by calculating for this one, which is now 7 to the first. So 7 to the first mode 15. And the next term is the 7 to the second to mode 15. And then we know that it is 4, not 49. And then final, and the next term is the value corresponding to value 3. And then we will obtain for 13. And what happens for the next term? We know that these remainder will repeat every fourth time. So we will obtain 1 and 7, and the other term will be 4, 13. And if we continue, then the same remainder will appear and again. And if we keep doing that, at the end, we will have the final last 4 term, which will look like this one. So we almost obtained the final result, and you might be wondering why I wrote down all of these in this pattern. But you might note that for this term, there is common factor of 1. What about this one? This one also has the common factor of all 7. So what we can do is for this term, we can rewrite or express all the summation of this one after we factor out this encoded register. So it will appear as the summation of 0, 4, 8, and so forth up to 252 tensor product with one in encoded register. Then what about the next term? This one has the common factor of 7, and then it will appear as the summation from 159 up to 253, and then it is tensor product with the 7. What about the next term? Yeah, it will be similar. So now it is factored out with the 4, and finally the last term has the 13 in the encoded qubit. Here, what you should note is that whichever term you have, each of them has the value which has a difference of 4 for each of the term. Yeah, so yeah, if if I assume that yeah, before I continue any further process, assume that I just measure the value of only the encoded register, then I might get one of these 4 possibilities from between either 1 or 7 or 4 or 13. However, whichever I obtain, I know that the ancillary register part still have this pattern, and then I can summarize this pattern as that you will have the superposition of all the value with the difference of 4. Yeah, so yeah, whichever you obtain, your starting value might be different, but the difference between each of the component are exactly 4. Yeah, so that's and then what we really want to obtain is this period encoded in this pattern or in whichever pattern here, and then that's where the quantum Fourier transform helps. So this is just a copy of the result from the previous page, and then yeah, let me just somehow plot or visualize this state. Yeah, so yeah, one of the typical way to plot this one is like this one, and so yeah, we will have some non-zero component in front of 0 state, and then 4 state, and then 8 states. So yeah, this one is actually the probability of measuring this one. Yeah, so it is the squared value of the coefficient. And then here, yeah, when I was explaining all this, I intentionally omitted the normalization factor for the clarity. But yeah, you can just think that there is some normalization factor, and then yeah, if you include those factor in the probability calculation, then you will obtain this kind of plot. Here, I'm just using only up to 64 input instead of the 256 input because it looks too crowded if I just plotted everything here. But the point is, whether I'm plotting for this one or the second one or whichever I do, they will look similar to this one. And moreover, if I calculate the discrete Fourier transform, and then their final result looks very similar to each other. So yeah, if I just apply some Fourier transform, then what I generally get is this pattern, and then if you are not comfortable with the Fourier transform, then yeah, probably it looks a little bit weird. But yeah, I will explain more details about the discrete Fourier transform, and then discrete yeah. I think yeah, not every student learned about the discrete Fourier transform. If you are electrical engineering major, then probably you learned about the discrete Fourier transform in the signals and system class. But for the rest of the student, probably you are you are more familiar with the conventional Fourier transform. Yeah, so if you just do the discrete Fourier transform, you will obtain this kind of result. And then here I'm plotting this kind of situation as this kind of vector. So even though here I said it is frequency, it is actually not just this value less than 1, but it is actually appearing as 0, 64, and 128 and 192. And the difference between this first line and then this second line is that if the difference is the second line, all the components in the second line is shifted by 1 from this first sequence. And then in Fourier transform, if your sequence is shifted by 1 or by some constant, then they generally appear as the additional factor multiplied in front of this value. But the location of each of the these bases does not change. So if I keep doing this, then again, for each of the line, your basis vector won't be changed, and then all what changes is only the this phase vector. And then right after the quantum Fourier transform, what we do is we actually measure the quantum state, and then if we measure, then we will obtain one of these, and then you know that whichever state we were left, the the possible output in this measurement is either one of these 0, 64, 128, or 192. And then once we obtain one of these value like 129, then there is some way to calculate this kind of ratio. And then from this ratio, we know that the denominator is number 4, and then this one eventually corresponds to the period which we were looking for. So overall, we need some explanation about the discrete Fourier transform. So that's what I'm going to do in the next page. Before we start to discuss the discrete time Fourier transform or discrete Fourier transform, let's first consider about the continuous time Fourier transform. You are familiar with the concept that any arbitrary function, something like something I don't know, whatever it is. Let's say that this is somehow periodic function, so we will continue to have additional similar probably then this will continue something like this one. And then according to the Fourier transform for the continuous time, then we learned that this one generally appears as the sum of the these multiple different sinusoidal curve, like this curve, and then there will be another sinusoidal curve, but with the higher frequency, like this one, and something like this one, and so forth. So this any arbitrary function will appear in principle. This can appear as the summation of all these components, and then so if I call this function, let's say that the period is t, then this function will appear as the 2 pi over t multiplied by t, and then let's call this function as s1 of t, and then for the second term, second function, yeah, it is the frequency of this curve is the twice of this curve, so it will be something like 2 pi times 2 over t, and then let's call this one as s2, and finally for the this one it is the 2 pi times 3 over t, and let's call this one as s sub 3, and so forth. And then what the Fourier transform says is that in principle, any arbitrary function like this one can be expanded as the superposition of all these components, like S1 t plus S2 t and S3 t and so forth. And then of course this one requires some different size of the coefficient C1 to C3, C2, C3, and so forth. Then how can you obtain this C sub 1? Well, yeah, this value can be obtained by multiplying f of t to the S sub 1 and then integrate over the one period, and then yeah, divide this one by uh, divide this one by time t, and then yeah, there might be some additional factor which I cannot remember exactly. So yeah, I just use the tilde. But the point here is that if you calculate this kind of integration, then what happens is um, for the first term, because it is multiplied by s sub 1, so the multiplication of this one and then integration will actually generate some non-zero value. But if you multiply s1 and s2 together, and then that means that, as you can see here, while the S1 is the single sign, only the positive value, S2 changes from positive value to negative value, and it keeps changing. So if we multiply them together and then take the integration, then they will just cancel with each other, and then eventually the term containing here will become zero. And then if you multiply any of these with another, and then take um, um, the integration, then all these terms will disappear. So this is the most efficient way to calculate, obtain this coefficient. And I think this kind of calculation probably reminds you something. It was probably the same process when you are expanding your any arbitrary vector in terms of the orthonormal basis. And then the reason we use this kind of sinusoidal curve is because when we multiply them together and then take the integral, then the different functions will always um, 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 leads to zero value for the integration. So that's exactly like taking the inner product between two vectors, and then yeah, and if those two vectors are orthonormal basis, then they just disappear. And then if you take the inner product between inner product of the same vector, then that value becomes 1, and then that one somehow remains, and then all the other terms just cancel. So that's how you can obtain. So this function works exactly like orthonormal basis. And then once we expanded any arbitrary function like this one in terms of this, then um, the so yeah, you can basically think that each of these function as a vector, and then this is some arbitrary vector f of t, and then yeah, we just expanded in terms of expanded this vector in terms of the basis vector, like this one. Now yeah, what is the discrete Fourier transform? It is kind of sampled function like this one. Yeah, so instead of having this entire continuous function, we might have only these values as a value, like yeah, each of these, and then yeah, we will also sample for the basis function, like this, and then for the other things, and then these are the sampled point and so forth. And then for this one, yeah, we will also have this value. So this is one way to consider the discrete Fourier transform compared to the continuous time. So let's yeah, based on using this concept, let's consider about the discrete Fourier transform. So if I go back to the discrete Fourier transform, then it can be somehow considered as the sampled value of some continuous function. And then, yeah, if I have the sample of n samples, then it can be considered as the n-dimensional vector space. And then each of these sequence which might be the sampled value from the continuous version might be considered as the vector in the n-dimensional vector space. And then now let's think about the n-dimensional vector space. Yeah, for this vector space, one option to consider the basis is just a typical basis, like only one of the component is one and all the rest of the values are zero type. But this is not so much of interesting because it doesn't help. It doesn't give us too much of the information. So another type of the nice basis in this vector space is that it should be also normal. And then yeah, if you define the new basis vector as this way, and then we are assuming that this k value can change from 0 to less than 1, then this k value appears in each of these exponent part. And then what we can see is that all of these vectors will be orthogonal to other bases with a different value than k. Well, yeah, so probably this still doesn't, yeah, this might not sound familiar to you. So let me give you some example. Let's say that we are considering n equals n equals number 8 case. So what is the vector? Well, yeah, there will be 8 orthonormal basis, and then for the k equals 1, then what I have to do is replace this k with 1, and then I just calculate all of these value. And then the problem with these values are these are all complex number, so it's not easy to visualize this value. But we know that from the Euler relation, um, the real part of each of these is the same as the so the real part of this is that it will be appear as a cosine minus 2 pi um, um, yep, times 1 over 8 multiplied by 1. And then if this k value changes, then this part will be replaced by k. So now, yeah, this value works as something like this value um, serve as frequency, while the second this component works as time. Yeah, so this is almost like a cosine 2 pi over 8k times t, and then yeah, here we are using t value from 0 to 7. So if I just plotted this cosine function, then it would look like this function, while for this discrete Fourier transform vector, we are only considering the sampled value, like each of these value. So that's why we have only these components. But the origin of this discrete Fourier transform can be considered as the sampled version of this continuous function. And then we can also consider some another vector with different k value. So if we consider when k equals 3, and then if we plot the real part of the each of the component again, then it is actually the sampled version of this this kind of higher frequency sinusoidal curve with a higher frequency. And then yeah, we are just considering each of these sampled value. So and then if we have this kind of definition for the basis, then to verify that this is actually also normal basis, what we have to do is we have to calculate the inner product. Then how is the inner product defined for this kind of vector? Well, yeah, you remember that if each of these values are the complex number, then when we are calculating the inner product, we should not forget that we have to take the complex conjugation for one of the vector. So this is a definition of the inner product. Once we define the inner product for the new vector space, the next thing we want to check is that whether the given vectors or the given basis vectors are really also normal. So if I just use the definition of the inner product introduced in the previous page, then we have to use for each of the component of this one, this vector, it would look like a 1 over square root of n, yeah, e to the minus 2 pi I k prime times j over n. Yeah, so that was the component for each of the component for this vector. And this vector also has the similar component, but now because we are taking the inner product, I have to calculate. I have to take the complex conjugation. So yeah, this minus sign will disappear in front of here. So yeah, the component corresponding to vector k appears like this one. Then yeah, once they are multiplied, we have to add up all the terms. Yeah, so that was the definition of the inner product in the new vector space. Then yeah, this part can be simplified like this way, because a lot of parts are common in these two vectors. And finally, we can we can replace the this complicated looking term just with the alpha, and then alpha is again defined as this one. Then yeah, let's check what happens if the k and k prime are the same. In that case, because k and k prime are the same, this becomes 0, and then the overall exponential term becomes 1. So the this inner product will just turn into the summation of 1 over n different j. And then the answer should be the overall summation of this one means that the total will be n, and so n over n becomes 1. So what does this calculation imply? So what we did was, for the same vector, we calculated the inner product, and then the answer is 1, which means this vector is normalized. So what about what happens if these k and k prime are different? In that case, of course, alpha won't be 1 anymore, because this is not 0, this exponent part. So we have to actually calculate the geometric sum of this sequence. And then we know that we already learned the summation of this geometric sum of, can be expressed in this way. So the next question is, what is alpha to the n? And the answer is, because alpha is defined in this way, so we have to we are taking the power of n of this component, and this one will just cancel with each other. So the remaining part is that only this component, and we know that this k and k prime are integers and they are different. So this part is actually the integer, and then it is the integer multiplied to the 2 pi I, and that means that it is just a um, um, yeah. So the um, yes. So sorry. Yeah. So it is the even integer multiple of the pi, which means that entire expression of this one simply becomes 1, right? So alpha to the n is 1, and then that means that this is 1, and then 1 minus 1 will be 0. So the overall inner product becomes 0. So what does this mean? They are orthogonal to each other. So it is normalized, and then they are orthogonal to each other, which means that the overall k vectors are also normal, and then they are almost they are complete, because we know that for example for when capital N is 8, then we know that um, each of these vector are expressed as the n numbers, 8 numbers, and then that if we plot these that kind of distribution in this plot, and then if we just plot only the real part, yeah, then they look like this one, and then as we increase the so as I mentioned, this part somehow corresponds to the frequency. So as we increase the frequency, then the oscillation, the speed of oscillation, or the um, um, yeah, uh, they will oscillate more often as we increase. So then the next question is, um, we know that because these are only composed of 8 different numbers, so the dimension of that vector space is only 8. However, if we write down this expression, then there is no reason why k should be only limited to less than 8. So from k can be any value from 0 to 7, but that's not the only option. We can also consider k equals 8 or 9 or whatever value. So does that mean that we have even larger dimensions with this basis than the original space? Of course, that doesn't make sense. And then how can we explain such kind of discrepancy? Well, so what happens is, if we have any value, any k, which is larger than capital N, then for example, we can split the k value into component which is larger, which is the integer multiple of n, capital N, and then the remaining value which is between 0 and less than n. Then the frequency component will appear in this way, and then this exponent will be decomposed into the product of these two factors, and then this factor just has the similar component like before, like here. And what about this one? This one says that they are just the n, capital N, so they will just cancel each other. And then now the j is the integer. So again, it is 2 times integer, and then it is multiplied to I. So eventually, this term becomes 1. So we will be just left with this one. So this is exactly the same component as we expressed with this this vector. So yeah, it looks like that. So it is kind of repeating the previous orthonormal basis once we found all 8. Then there is a little bit confusing part because we know that, as I mentioned here, this part where this component corresponds to frequency. And as we increase, we know that typically these sinusoidal curve will oscillate more often as we increase the frequency. And if I keep increasing this frequency, then it should oscillate much faster. And then how can it be the same as the already existing one? The answer is, as you can see here, if I increase this frequency component, then you can see that it is actually, if we plot the continuous wave, then it is actually oscillating much faster compared to this case. However, because the timing we are sampling is actually fixed, so if we just sample all those sample at the fixed timing, then they will, yeah, even though the underlying curve is oscillating much faster, the sample result actually looks exactly the same like this one. And even if we increase the frequency, the final result is actually following the pattern of the lower frequency counterpart. So again, yeah, this is also oscillating much slower compared to this underlying oscillation. And then yeah, this kind, yeah, because this situation, again, if we only consider the frequency, this these cases seems to have higher frequency, but the resulting vector of which is only composed of 8 numbers, then they actually look exactly the same like lower frequency vectors. So yeah, that's your curiosity or question. And then this kind of phenomena is actually has a name in digital signal processing, and then it is called as aliasing. Yeah, so I hope this somehow clarify some of your question. Now, because we found out that this vector defined in this way is a good orthonormal basis in the vector space composed of the n value, or n, yeah, in this case it might look like a row vector. So yeah, this even though it is not like a 0 1 0 0 0 or 0 1 0 0 type, but still it is a good um, um, complete basis for the new vector space composed of n numbers. And then when you are given, assume that you are given some sequence, some arbitrary sequence of numbers, which is composed of capital N numbers, and then you can also consider, because you can consider this one as a vector. This vector, yeah, you can also think that this vector can be expressed as the weighted sum of basis vectors in this new basis. Well, yeah, so yeah, you might be wonder why we are doing, but yeah, let's see whether that makes sense. Yeah, so here is the plot of the K0. Yeah, in when we only plot the real part for this, and then yeah, for K1 vector, K2, and K3 vector. So these are the, yeah, these are the four bases, or the complete basis of the of this basis, this vector space, when we are considering only capital N equals 4. Yeah, so this is complete because we know that it is when capital N is 4, then it is its dimension is only 4, and then that means that we will have only 4 linearly independent and orthonormal basis. And then we just found all of this. Then the next question is, if we assume that we are given this this kind of sequence, some arbitrary sequence, 1 5 1 5, then the question is whether we can decompose this vector as the linear combination of these four vectors or these vectors. Then a 1 5 1 5 vector can be plotted like here. So in this case, yeah, this is this is 1 and this is 5 and 1 5. So if you look at the data, then you can see that this one has some kind of symmetry with respect to the value of 3, and then you can see that these sequence 1 5 1 5 might be decomposed into two types. One is that because with respect to this 3 line, there is a value which is behind -2 lower and +2 higher, and -2 and +2, like this value. And then you might also consider that this is the 1 5 1 5 distribution is the summation of this this distribution and the 3, yeah, every value 3 3 3 3. Then yeah, this can be this 1 5 1 5 value can be considered as the summation of these two types. And then for this -2 +2 -2 +2 is actually related to the sequence of this one, because for this case it is actually, except that it has a smaller scale, 0.5, and then its sign is opposite, but the pattern is actually the same as this one. So yeah, and then we know that this sequence is 2. So you might say that this is actually the -4 times 2 vector. And then what about this kind of distribution? It is constantly 3, and it is also related to this vector. And then in this case, the value are constant 0.5. So the ratio is that 6 times. So you might also consider that. So this vector is represented as a zero. So you might also say that this is the 6 times the 0 vector. So overall, we might claim that the 1 5 1 5 vector is the summation of 0 vector and 2 vector, and then the coefficient in front of it is 6 and -4. So in this case, how? Yeah. So here I just found out the component just by using my intuition. But is there some systematic way to find out these coefficient? And the answer is yes. And then what we can do is use the inner product with the basis vector. So if you remember that in the typical situation, in a typical vector, to find out this coefficient or the probability amplitude, then what we can do is take the inner product between 0 and x vector. Probably sorry, yeah. So yeah, in this case, so if you remember the definition of the inner product, then what I have to do is take the complex conjugation of this sequence and then multiply them together. So it is 1 over 2 and 1 comma 1 1 1, and then yeah, if you take the complex conjugation, it will be the same as this one, and then I have to calculate the 1 5 1 5 um, sequence, which is the X factor. And in this case, we know that the, let me change the color now. And then in this case, it will appear as the 1 over 2, and then I have to multiply each of the component. Yeah, so it is 1 plus 5 plus, again, it is 1 and it is 5. So 1 plus 5, so it is 6. So that's how we can obtain the 6 value, just by calculating the inner product. And then we can also calculate the coefficient in front of 1, which turns out to be 0 in this case, and then we can confirm that it should be 0, because if I calculate the, so um, what I need to do is use the k equals k equals 1 vector, but before I write down, I have to also calculate, find out, take the complex conjugation. So its complex conjugation is 1 plus I and minus 1 and minus I, and I have to also take the inner product with the 1 5 1 5, and then the answer is 1 over 2 times 1 1, and it is plus 5I, and it is minus and this is minus 1, and it is minus I times 5, so minus 5I, and then they will just cancel with all the others, and then it will become 0. And then to find out this minus 4, then what you have to do is, again, take the inner product with the basis factor 2. And so if you just continue, then you, in principle, you can find out each of these components. So what did we do? What we did is this kind of calculation is exactly the same as what we did when we wanted to find out this C1 value or C2 value and C3 value. What we have to do is multiply the given vector with the sinusoidal curve, and then we just take the integral of this value, and then so for the discrete version, instead of taking the continuous integration, what we do is just the sum of each of the sampled value, and then just following that rule, then in principle we should be able to find out C1, C2, C3, and so forth. So what we just did is exactly like finding out the coefficient in front of the basis vector when we are given some arbitrary vector. So this is exactly another types of the linear algebra. And then another thing I also want to emphasize is that when we find out uh, um, coefficient like 6, then what's the meaning? That means that for this vector, if you remember the result, then what we had was our original arbitrary vector, like a 1 5 1 5. It actually had some kind of non-changing value, and then we generally call this one as a DC component. The DC means the direct current in the circuit analogy, but people generally say that if you have some constant components, then you say that it is a DC component. So if you remove this DC component, what you are left with is this kind of oscillating behavior. Well, maybe I should draw in this way, because it was the origin of that such kind of distribution came from the oscillation, like this oscillation. But because we were just sampling, so we only had this value. So the origin of this kind of distribution is oscillation. And then what we found out is that this 1515 has this kind of frequency, or they are repeating the same value every twice. So this one actually implies that it has the frequency of yeah, to convert this one into frequency, then I should be careful. But I can say that they repeat, the period is 2. So whenever we are finding out the coefficient using this new basis vector, or this is actually called as um, the Fourier, yes, some kind of sinusoidal basis, then what we did was to find out what kind of frequency component does the this this arbitrary sequence of number has, and then that's exactly related to the period finding problem. Then, if we go back to the previous example, then we were left with some kind of vectors, some vectors like 0 plus 4 plus 8 plus 12 plus, and so forth. So we know that, yeah, we can say that it has the period 4. But how can we find out the period 4 mathematically? The answer is we can consider this kind of vector as a sequence of the number, and then the sequence value, it comes from the coefficient or probability amplitude of each of the basis vector. So in that case, 0 vector has coefficient of 1, and the 1 vector has a coefficient of 0. 2 vector has also coefficient of 0. 3 vector has 0, and 4 vector now has 1 again here. So it is 1, and again 0, 0, 0, and 1, and 0, 0, 0, 1, and this kind of, yeah, it will continue. So we have, yeah, in that previous vector, we had, yeah, you can imagine that we have this kind of sequence, and what we are trying to do is decompose this vector, not this vector, yeah, but some very long vector, and then we want to decompose this vector as the weighted sum of this basis vector. So what we are trying to do is find out the coefficient of each of these vector when you are given this vector, this sequence of vector. So that's what that is, and such kind of calculation is called as a discrete Fourier transform. And then what we have to do is, if we are given any arbitrary vector like this one, then we have to find out the coefficient, like 6 and 4 minus 4 in this case, and then for this case we have to also figure out what is the corresponding vector. And then what we have to do is we have to perform this discrete Fourier transform in within the framework of the quantum mechanics. Or, yeah, in other words, we have to perform this kind of discrete Fourier transform in the within the Hilbert space we have been considering. So if I summarize what we want to do, and then what is the meaning of the discrete Fourier transform means is that when we are given some arbitrary random number sequence, something like from 0, x naught, x1, x2 to x sub n minus 1, then we want to find out the hidden period in this sequence. Then let's get back to what I just showed you in the previous page, that if I have some kind of some random number sequence, and then assume that this this sequence is expressed as some kind of vector in the vector space with the dimension of 4, then yeah, I showed you that this can be expanded as the summation of linear superposition of 0 and 2 basis vector. And this is this 6 or number -4 is actually the coefficient of each of the basis vector. And then if you remember how we can find out the each of the these coefficient component, then for example, if we wanted to find out this -4 or C2, then what we do is, if I wanted to calculate the C2, then it is calculating 2 and x vector. Then how is the vector 2 expressed in terms of the row vector? Then it was something like square root of, if you remember the definition of the that Fourier basis vector, then it appears like a square root of capital N, which is number 4, and then it was e to the 2 pi I, and it is because it is 2, so we will have 2 over, oops, so it will be 2 over capital N, sorry. So this is over 2 over capital N, which is 4, and then we have to multiply 0, or yeah, let's say yeah, we multiply 0, and then we would also have the next term was 2 pi I, and then it is again 2 over 4 multiplied by 1, and then the next term was e to the I 3 over 4 times sorry, this should be 2, and it is multiplied by 2, and the last term was 2 pi I 2 over 4 times 3, and this value is multiplied by x the vector x, which is that has a component of x0, x1, x2, and x3. And if I just expand the entire product, then x0 will be multiplied to this component. So it is similar, equivalent to just calculating the well, yeah, in that case I can somehow rewrite this front part like 1 over 2, and it is x naught times x naught times this value, and then I should also add and then this x1 will be multiplied with this guy, so it will have x1, and then this x2 will be multiplied to this one, which is the x2, and then finally the last term x3 will be multiplied to here, so I can say that it is x3, and then yeah, we can erase this one. Yeah, so this is the expression to find out C2, and then C1 or C0 will be almost similar to this one, but only this value, this 2 value here will be replaced by either 1 or 0 or 3. So if I just summarize or clean up this expression, then it will look like this one. Yeah, so this is exactly what I rewrite. Yeah, I just basically copied all of this, and then yeah, here I will start to use the y sub 2 rather than c sub 2, because I want to follow some of the other notation. And then yeah, you can also see that what is going on here. Yeah, so what I do is that when we are given from x naught to x3, then what I'm doing is I'm multiplying this x naught, x1, x2, x3 to each of these value which appears here. Then what about the C1 or y sub 1 or C naught or y sub 0? Then they will appear like this one, and then each of the term corresponds to yeah. Yeah, so yeah, in this case, y sub 0 or y sub 1, or yeah, each of them has different index appearing here, and then the y and then those in the summation, what corresponds to each of those index for the x value is the number which is multiplied to here. Yeah, so this is the typical shape of the discrete Fourier transform. And then what we need to do is to figure out what kind of frequency component does this sequence has in well, yes, so what we want to do is find out the period embedded in this given sequence of number, and then in this case, by multiplying these sequence to each of these value, then the final number you will obtain is actually corresponds to the coefficient of the basis vector, and then that's exact that basically represent how much of the component are embedded inside this given sequence, and then that's that also, and as long as this one is not a 0, that means that this sequence has the some basic sequence which has the period of this case 4, or this case period of 2, and then for this case different period and something like that. So then what is the goal of the quantum Fourier transform? Yeah, so as I mentioned, yeah, what I'm calculating here is typically called as the discrete Fourier transform, which is typically performed on the digital computer. But here, what I want to do is quantum Fourier transform. So we have to decide, and then quantum Fourier transform will be described as some kind of unitary function. So what I have to do is define the input of that quantum Fourier transform and then output of the quantum Fourier transform. And then here, I will define that the input of the quantum Fourier transform, or QFT, is that the input will be given. Yeah, so what we want to do is find, perform the discrete Fourier transform on the this sequence. And then if you are given this sequence, then you will first construct the quantum state which has each of these value as its coefficient of the vector. Yeah, so when again, when you are given any arbitrary sequence, then you first want to build this kind of vector, and then after the process of the QFT, then you hope that your final output state or final vector will expressed in this form, meaning that the corresponding result of the QFT will appear as the coefficient of each of the basis vector. So how can we implement this kind of Fourier transform, or this kind of unitary operator? So to figure out how we can transform this kind of input to the final state of this form, in the next page, what we are going to do is replace this y naught with this expression, and y sub 1 with this one, and so forth. So let's do that. Yeah, so if I replace the y sub 0 with the expression given in the previous page, then yeah, what here, if I just replace then I will have 4 terms, and then I intentionally expressed this term multiplied by this component in this way so that I can find out some kind of pattern. And then if I replace the expression for the y sub 1 from the previous page, then this term can be also expressed as the sum of these four terms and so forth. So if I just keep replacing the expression in the previous page, then it will also appear like this one. And now maybe you note that there is some kind of pattern. Yeah, so even though these are all multiplied by or all the terms having the zero basis vector, there is a component that all of these four terms are have the x sub naught. So in principle, I can collect or factor out x naught here and then re-express the remaining part as this kind of summation. And what about the next line? Yeah, it also has the similar result like this one, and then this one also has the similar pattern, and the final term also would be expressed as the summation of all these. Oh, I forgot to have a plus sign in front of it. Yeah, something like this one. And then um, what does this mean? Well, we know that x naught, x1, x2, x3 were the sequence of the input. And then we started with this kind of initial quantum state. And then after the QFT transform or QFT unitary transform, yeah, the final state should appear like this one. And then what this means is that when we started with this one with the x0, x1, x2, x3, that means that this zero vector, initial zero vector, should be mapped to the entire expression like this one, and then the one should be mapped to or transformed into this summation. Oh, I had this plus sign, yes, so I didn't need the plus sign here. Sorry about confusion. Yes, sorry. Yeah, something like this. So and then does this remind you any of the previous relation? If you remember what happened to the Hadamard gate, then the Hadamard gate operation is generally described as um well, yeah, let me use, yeah, so um zero vector and then one vector transformed by the Hadamard gate, like um it is transformed to 0 plus 1 and 0 minus 1. And then this kind of mapping is more complicated, but except that complexity, it is actually exactly the same type of transform. Here, we were only working in the two-dimensional space, and here we are working in the four-dimensional space. And if the capital N increases, then we would have more terms, and then we would still have this kind of transformation. So if you remember that this kind of transformation or Hadamard gate, the purpose of the Hadamard gate was the basis transformation. So in some sense, quantum Fourier transform can be also understood as the basis transformation. So what we have to do is how we can implement such kind of transformation. So as I mentioned, yeah, what we need is transform some of the computational basis to the some of the not the yeah the what we have to do. Sorry, what we have to do is we start with the computational basis, and then we have to transform this one into the summation of all the computational basis, but with different coefficient. And then there should be some kind of rule for this kind of transformation. So the next question is, how can we implement this kind of transformation using the quantum gate? So the circuit to implement such kind of quantum Fourier transform looks like this one, and then yeah, probably this looks very complicated at first. So yeah, to fully explain this one, I will need more time. So I will explain further about the circuit in the next lecture. But let me summarize what we are trying to do up to now. Yeah, so I started with the introduction of the discrete Fourier transform, and then discrete Fourier transform is a concept in the classical classical computation. And then the challenge in that case is that when we are given some kind of sequence of numbers, then we want to find out some kind of hidden period inside this sequence. And the way we do is we consider this one as some kind of column vector or row vector, and then assume that we will try to expand this vector, or this vector. Yeah, here I'm representing this sequence as a vector, as the linear combination of the another basis, which generally called as the DFT, or discrete Fourier transform basis. And then what we have to do is find out each of these coefficient, and then the meaning of this coefficient is how much of the component we have this basis, and then what this basis means is that x vector has that amount of period inside the sequence. So as long as this value is not zero, then we this sequence originally has such kind of period inside. And then if we just write down the expression for each of these coefficient, or y sub something, then it will be, yeah, because we know the each of the value each of the sequence, or the sequence of the discrete Fourier transform basis. So if we just plug in all those expression, then we would end up with this kind of y sub k um, should appear in this form. And then here, yeah, each of these component x sub 0 to x sub n minus 1 will appear as some vector in this summation. So that's the classical DFT. Then what is the quantum Fourier transform, or QFT? In this case, we have to, yeah, in quantum process, we generally have to define the input and then output vector. And then in this case, the input vector will be expressed as this kind of superposition. And for this case, the coefficient of each of the computational basis is um, replaced by this of the this sequence of the input, and then the output state will be the um, will have the this result of DFT as its coefficient. So to implement this one, what we have, yeah, so what we want is we want to transform this state into this state. But in the previous page, I showed you that this expression can be re-expressed in some other way, and then that means that this kind of transform means that each of these computational bases should be transformed into the linear superposition of all the bases with this kind of special coefficient in front of it. So what we have to do is in to implement the QFT circuit, the function of this circuit should be that if we provide this kind of computational basis, then that computational basis should be transformed into the summation of these vectors. So that was the summary of the QFT. Then why did we need the QFT? First of all, yeah, if you remember, yeah, we basically started with the Shor's algorithm. And the Shor's algorithm is composed of two steps. The first step is that where maybe I should say three steps. The first step is to create all the superposition of all the possible exponent, and then we apply all those values to the circuit, which will try to calculate the some r to the um, r to the n type of calculation, and then finally that result of the such calculation contain some vectors like 0 plus 4 plus 8 plus something like this one, or sometimes it has 1 5 9 plus something like this one. And then we can consider that this sequence actually implies that this means that it has a 1 in front of 0, and then 0 in front of 1, and then 0 in front of 2, and 0 in front of 3, plus 1 in front of 4, and so forth, and 0, blah, blah, blah. Yeah, so this one exactly means that when we have sequence of 1 0 0 0 1 0 0 0, something like this one, and then what we are trying to do is find out the hidden period inside this sequence. So that's exactly um, um, so yeah, that's exactly what we do with the discrete Fourier transform. And then the result, yeah, and then once we can obtain this value, then that corresponds to finding out the hidden component of the period of the some hidden sequence, or some hidden um, TFT basis. Yeah, so that's what we are trying to do. Yeah, so and then once you find out some non-zero value, then basically you found out some period inside this sequence. So we will continue about the discussion of the QFT in the next lecture.